Hello guys, I wanted to continue and follow up on what we discussed last time with the DH parameters and how to first of all place proper DH frames, and after you place proper DH frames you do the actual transformations, and ultimately you will be able to obtain the homogeneous transformation between any two frames that are on your robot. This is an example that we did last time, and we said that the first thing that you have to do when you are placing your DH frames is that you have to place the Z vectors, right? So the Z axis or the Z vectors are the axis of actuation. And if I have a rotary joint, the Z axis will always be along the actuator. If you have a motor, basically, the Z axis will be along the motor shaft. If you have a prismatic joint, then the Z axis will be along the piston direction. In this case, we have, this is a 2-degree of freedom system. We start by placing our base frame, essentially. So Z0 also here is along the motor, basically, which is rotating the first link. Then I'm free to select X0, Y0. Second thing is I'm gonna place my Z1 and Z2, basically. In this case, it's parallel to Z1. And then I'm going to be placing my axis, right? And then we said for a frame to be a proper DH frame, not only you have to put your Z axis along the actuation axis, but also your X axis have to be perpendicular to your existing Z axis and also the previous Z axis. So here you see that X1 is actually perpendicular to Z1 and also Z0. And once you have these two vectors, basically now you can locate the origin of that frame, and then you can pull the coordinates of the origin of the cycle frame from your DH01, for example, right? And so on and so forth. Okay, so this is what we did. We basically built our table. We said A is going to be the distance between the Z-axis. In this case, it would be the length of the first link. Alpha is 0 because Z-axis are parallel, right? So you would only have an alpha to be like, for example, 90 or minus 90 if your Z-axis basically changes direction or changes orientation. For example, you would have, your first joint, drawing it here. If I have a robot like that, so this is my first joint, so my Z-axis is like that. Then I could have basically another joint like this, for example, right? And then this is my Z1, right? In that case, basically my alpha would be 90 degree. All right, my D is the offset between the x-axis, basically. So here the x-axis are in the same plane. And then I have my theta, which is going to be the angle between x0 and x1 measured about Z0, right? So by how much I'm rotating x0 to x1 about the Z0 axis. So once you have that, you can build that table, and then you can plug these into your DH transformations, and then you can calculate like DH01, you can calculate DH12. So each row in that table basically will give you a transformation between link 1 and link 2, for example, such as this guy, for example. Okay. All right, and we also did that example. Make sure you guys are watching all these videos and getting up to speed because we will probably have our exam somewhere around mid-October, almost in like 2 weeks from now. So make sure you are very familiar with how to solve or how to obtain the homogeneous transformation between any two transformations, how to find the rotational matrix, how to find the coordinate of another frame with respect to one frame, how to basically do transformations between any two frames, etc. And I'm going to be posting the assignments has already been posted, but I will be posting the solutions actually sometimes in this weekend. Okay, so what I will do today is I want to go over the robotic wrist configuration, and basically what we're trying to do here is this is like a turret, right? And my goal is to be able to point this link, right? I want to be able to point this and the vector in any direction that I want, right? And then if you think about it, basically all you need is how many angles to be able to do that. You will really need 2 angles, right? For me to be able to, position this vector, right? First of all, I need to know this angle, theta 1, right, which is the angle for this guy, right? So this will define along which direction this guy is pointing. And the second thing that I need is to be able to point the actual orientation of this guy, right? The last angle basically is going to control the roll, right? So essentially we have yaw, pitch, and then roll. The yaw, in this case, is going to be what? The yaw is mainly going to be theta 1 here, right? So, you know, if theta 1 is 0 basically, then what? Then x1 is going to be here, right? And if x1 is here basically, then this guy is going to be pointing toward this direction. But it doesn't really matter. You know, theta 1 will, so there would be some offsets in this case, but theta 1 will always essentially control the direction of this guy. Okay, direction in the horizontal direction. And then the second angle that we want is going to be theta 2. And theta 2 will control essentially the pitch of this guy, right? Or, you know, how high this guy is pointing. And then theta 3 will actually control the roll. Okay, so the roll is, so I'm rolling the end effector about itself. Theta 1 will control the yaw of it. So, you know, how am I rotating this guy in what direction? And then the pitch is the kind of the elevation angle. Sometimes it's actually called the azimuth angle, is referred to as the pitch. All right. Let's actually look into the frames, and here we actually have proper DH frames. Let's look into it in more detail. So this is my first link. I put Z0 basically along my axis of actuation. I put Z1 along the axis of actuation of the second joint, and then Z2 is the axis of actuation of the third link, right? And remember that, right? So Z0 always drives link 1, right? Z1 drives link 2. Okay, and Z1 is sitting on link 1, right? Z0 is sitting on the ground, right? Which is not part of the robot. Z1 is basically this whole thing basically being rotating, all right? The second step is we want to put our x-axis, right? So my x0 is free. I can put x0 whatever that I want. And basically once I have x0, basically I can find where y0 is. So usually we don't really need y0 because it's already defined by my Cartesian frame or my right-hand rule. So I place my x0. The second step is I want to place x1. So here I have to place x1 such that it's perpendicular to z1, obviously, because you have to have a frame here. But also it must be perpendicular to your previous z-axis, right? So x1 here is perpendicular to z1, and it's also perpendicular to z0. We're good, right? So now we can identify our origin for the second frame, or for the first frame, which is frame 1. Second thing is I have to basically, so I have, this is my z3, right? So I have to have my, well, I have my Z2, right? Z2 is here, right, driving this guy. So my X2 has to be perpendicular to Z2 and also Z1. So it actually must be here. So X2 is now locked here. And then a third thing is what? So I have my Z3. So we said always on the end effector, right? Link 3 of this robot, it's not driving any other action, any other link. It doesn't really have any axis of actuation. So a good, a good rule would be, a good thumb rule, for example, would be to actually put Z3 to be parallel or collinear with Z2. So then your X3 is going to be parallel to X2. Third step is we're going to establish what our theta is. We said theta is going to be always the angle between my x0 and x1 about z0, right? So x0 to x1, this is my theta 1. By the way, here x2, it could be in a direction and it will also be in another direction, right? It will only result in an offset, but it will always be a viable DH frame. All right, so theta 2 is going to be the angle between x1 and x2 in a counterclockwise direction, right? In the right-hand rule. So basically, I have this is my z1, and then my theta is going to be in that direction. All right, so it's measured right from x1 to x2, and then likewise now theta 3 is measured from. So basically, this is my x2. This is a representation of what x2 is. So this is my theta 2. So this is a robotic wrist basically, and the goal of the robotic wrist is I can solve for theta 1, theta 2, and theta 3 to be able to position this end effector right in any direction. Let me kind of draw it here. Okay, let me just do it like that. Okay, so this is my robotic wrist. So now I'm essentially, I'm able to point this vector in any direction, right? So now if I actually, let's say I'm projecting this guy over here, right? And this guy, for example, this guy is, let's say, my theta 1, right? Based on, you know, this frame that whatever the frames that I have here. So this guy basically controls the rotation where I'm actually pointing this guy, essentially referring to the yaw, right? This angle here is theta 2, and then this guy basically controls the pitch of this vector, right? And then the third one here, basically, right? It actually controls what? The role of the end effector. So essentially, now I'm actually able to position this wrist, right, at any pitch, any yaw, and essentially any roll, right? And what we usually do in the case of the robot, so the robot will have the first 3 axes to actually control the actual position of the robot, and then the rest is actually done to mainly do the orientation here. And then we're actually going to see in a second. All right, but this is a robotic wrist, and then when you place the H frames on it, what you actually end up with, let's actually look into it. Okay, so let's, yeah, so when we place the H frames, let's actually try to build that. Let's put some dimensions on here, and we have our D1, we said is going to be what? The distance between the x-axis. So it's the distance here between x0 and x1. How about alpha 1? Alpha 1 is going to be what? Alpha 1 is going to be the angle between Z0 and Z1, right? About x1. And D, so yeah, so D is the offset between the x-axis, which is going to be D1. A is the distance between the z-axis, is 0, right? And then theta here is whatever theta that we have. Now, what is rho 2 basically? Rho 2 is going to be the transformations between a frame 1 and frame 2, right? So what is the distance A? What is the distance between the z-axis here? Between Z1 and Z2, basically it's 0, right? Because they are collinear. Then alpha, what is the angle between Z1 and then Z2? About X2 is going to be 90 degree, right? So basically I'm rotating Z1 into Z2 about X2. So X2 is my positive direction. So when you want to do this, so this is my X2, right? So I want to basically, my thumb is going to be pointing along X2. Now, the rotation is going to be in that direction. So I'm rotating Z1 into Z2 by 90 degree. And then the third one basically would be simply the homogeneous transformation between the second and then the third, basically, which is simply a translation, right? And then here we have a distance of simply a D3, right? D3 and then theta 3. Let's actually look into it. All right, so looking into that again, so building the first row, we said frame 0 to frame 1, right? What is A again? A is the distance between the z-axis, right? So Z0 is basically intercepting C1, so it's 0. Alpha is what? What is alpha again? Alpha is the angle between Z0 and Z1 about X1, okay? So remember, it's about X1, not X0, about X1. So you basically, if you put Z0, it's going to be pointing upward, right? And then this is your Z. If you do a right-hand rule, basically, so this is my X, right? So this is my positive direction, right? In my case, I would rotate Z0 by either, in that direction, I would rotate it by 3 pi over 2, or I would rotate it minus pi over 2 to bring it to Z1. That is why I have minus pi over 2. All right? Third, we need the distance between x0 and x1, which is, you know, the geometry of that wrist, so d1, and then lastly is theta 1, right? And then theta 1 is the angle between x0 and x1. Okay, and again, x1 could be either in whatever direction that you have, right? But whatever direction that you have, you will actually write your theta 1 to be the angle between x0, right, all the way to x1 about Z0, right? And this is why this will always work, because we always require that x1 is perpendicular to Z0, right? To Z0, and then I know x0 is perpendicular to Z0. It means that theta 1 can only be one angle between x0 and x1, right? It will always be about Z0 because I'm always requiring x1 to be perpendicular to Z0 as well. Now let's look into row 2 again. So what do I have for A? A is a distance between the z-axis, so it's basically z and z and z, so it's 0, right? And then alpha. Alpha is the angle between z1 and z2, right? About what? About x2, right? Okay, so by how much do I need to rotate z1 into z2? By pi over 2, right? So you can see that if your thumb is along x2, so basically you are rotating in that direction. So this is my thumb will dictate my positive direction. Now I'm gonna look into the figure. I would see that, if this is my positive direction, like this rotation like that, right? If this rotates my positive direction, so I'm gonna rotate Z1 by 90 degrees to bring it into Z2. So this is why it's pi over 2, G is 0, and then theta 2 is theta 2, which is the angle between what? The angle between x1 and x2, right? And then x2 is obviously perpendicular to Z1, so it's gonna be this angle right here, okay? And when, on the exam, guys, I will ask you not only to obviously submit the online exam, but I would also ask you to submit your actual handwritten solution. All right. And so make sure when you are writing angles, right? So you never want to put me, like if I have like, two vectors, you never want to put me an angle like that, right? I will actually want to see the angle between exactly two lines. Okay. So this would be theta 2, for example. And it cannot be like just an angle like that. Okay. Okay, so we're good here. Now what we'll do is we'll actually apply the DH transformation. So now we actually have the individual rows. We can just plug that, and then where do I get this from? Well, we already have the DH function, right? And those of you who don't know it yet, so this is my DH, right? We have actually solved that before. Okay, so this is my DH, and then literally every time that I want to apply the DH transformation, I'm going to fill this guy up, and then this array here basically is a function of 4 variables, right? Theta, D, A, and then alpha. And we actually have this in every row right now that we have it. Okay, so this is the first row, etc. Second row, third row. So we have first one, DH01, DH12, DH23. Now we can actually multiply these. And when you multiply these, actually, you end up with D03, right? So this is a homogeneous transformation between the base frame and the end effector frame. What can I tell from this guy? What can I tell from this guy before we do another example? So what I can tell from this guy is that the first column, right, is what? Is my x-axis, right? So we were here, right? And then we said, I'm actually gonna redraw this one last time and make it slightly smaller. Okay, so this is what we had, right? So we had, this is my 0, 0, and then y0. And then here, what we did is basically we have, this is my z3, right? This is my z3, and then this is my x3, right? Okay, and then this is my o3. It doesn't, yeah, so this is what we have here. And this is my DH transformation right here. Okay, so okay, let's look into the first column up here. What does the first column mean? So the first column means what? Means basically now I actually have x3 in frame 0, right? This is my DH03. Okay, so this is basically my x3 0. The first column here basically is I have my x3 in frame 0. Second one is basically I have my y3 in frame 0, and the last one is basically my z3 in frame 0, right? And the other column that I have here is basically is going to be o3 in frame 0. Okay, so now I can actually tell a lot of valuable information. So one thing that I want to do is, I can find the origin of the origin of that frame basically with respect to the base frame, right? Given, some angles that I have and then some dimensions that I have here, right? And what we did basically, I think this guy was called D1 here, right? Okay. Okay, so one thing here is basically, you see here, basically I have 4, 5, 6. So here, what you want to do is think of 4, 5, 6 basically. So this is usually part of a 6-axis robot. And theta 4 here basically is meaning really theta 1. Okay, theta 5 is going to be theta 2. Theta 1 here is here. And then theta 6 is going to be here. All right. I'm just doing this right now as a representation just to show you what you can do with this, okay? Obviously, when you want to get theta 1 here, basically, you want to see exactly what your x1, where we had it in the previous figure. But what I want to show you here is what we can do is basically, let's say I would actually like to point this vector toward a given direction, right? And if I want to do this, basically, this is the vector that will actually control the direction of my wrist, right? So if I actually have this, then I can literally define where I would like that to be, right? And this is Z3 in frame 0. So if I actually, write Z3 0 to be, let's say, 1, 0, 0, what would that mean? It means that I'm trying to solve for, theta 1, 2, and 3. That would make what? That would make this wrist to point how? To point in my X direction. So the wrist will actually be pointing toward this direction, right? Okay, so this is just a representation for that. So if I actually have Z3 0, it literally means that this guy is going to be pointing toward that direction. Okay. And I could also have this guy to be pointing in any other direction that I want, right? So this vector literally will actually control how this vector is actually pointing toward. All right. So it turned out that we can actually use this guy to actually do the inverse kinematics here. And what happens in the case of this robotic wrist that we have, so it means that if Z0 has to be crossing Z1 and Z2 basically is also Z2, which is here, crossing the same point. So this point is actually called here a wrist center. So the wrist center is where all these vectors are actually intersecting. And when you actually have a robotic wrist, it means that the Z0, Z1, and Z2 are actually crossing in the same point at the wrist center. And when you actually have a wrist configuration that exactly looks like this, your homogeneous transformation will actually look like this. And you will be able to use this guy to be able to directly solve for cosine theta 5. Right? So you can start by using this guy to be able to solve for the angle on theta 5. And now once you have theta 5, basically you can use those two guys to be able to find what is the value for sine theta 4, for example, right? Or tangent theta 4 by dividing these two onto each other. Okay, and then from this row, you will actually be able to solve theta 6. So you can literally ignore these guys. You can use this column to be able to find theta 5, and you can use this row to be able to find. So you use this entry right here to find theta 5, right? So basically, we have cosine theta 5 equal to some value. This will give me the pitch of this guy. So I can solve theta 5. Then I can, so once I have theta 5, I can use this guy to be able to find my theta 4. So let's actually see how we can actually do that. What I'll do is let me kind of remap this into, just to avoid any confusion. Let me write that as H03. So if I do the homogeneous transformation, if I actually do this array, basically, I'm going to end up with what? I'm going to end up with cosine. Let me just write it like that. So C1, C2, C3 minus S1, S3, right? This is the first entry. And then what I have here is I have S1, C2, C3 plus C1, and then this guy is going to be S2, and then the third one is going to be what? Minus sine 2, C5, okay? On this row, I'm going to have minus C1, C2, S3. Okay, this is S3 minus S1. C6 is what? C6 is gonna be my C3. And then I'm gonna have minus S1. Minus S1. I have here what? C2, right? And then I have S3 plus I have C1 and then C2. Okay, here I have S5 is going to be what? Equivalent to S2 and then S3. Okay, let's look into the third row. I have C1, S, S2. And then I have S1, S2, and then I have C2. And then basically I have 0, 0, 0. And then let's just ignore the last one because we don't need it. Okay, so now let us say that I actually have a particular orientation that I would actually like to point my end effector toward, right? So what I'll do is I'm gonna say my, Z3 0, right? So I would like this guy to point toward, a given direction. And let's actually call this direction, ZX, ZY, and then ZZ. Okay, so this is the direction that I would actually like to point my vector toward to. So essentially, I'm pointing this guy, right, along this vector. Plain simply, okay? It means that this guy has to be actually equal to this, right? So what I'll do is, so I have my cosine theta 2, right? Cosine my theta 2 has to be equal to what? Has to be equal to my ZZ, right? Which is the direction that I'm actually pointing this guy. So now literally I can solve for theta 2. This is called the inverse kinematics of this. It will be actually equal to cosine of minus ZZ, right? Obviously this has to be normalized. So now we have solved for theta 2. How can I solve for theta 1? So one thing would be we can actually divide this guy over this guy, right? So if I divide this guy over this guy, so I have here S2 and then S2, so I will actually end up with S1 over C1 is going to be equal to ZY over ZZ, right? You guys agree? Which is actually equal to tangent of theta 1. Okay, so what we can do here is then theta 1 is going to be equal to inverse tangent of ZY over ZZ. Okay, so this is how we can, so now we find theta 2, then we can find theta 1. So in MATLAB, what you want to do is if you do inverse tangent, right, if the two here are negative, right, it will actually return theta 1 to be positive. What you want to do is you want to do theta 1 is actually A tan 2. Okay, so this takes arguments of two things, and you can put zy and then zx. Here, this function, if this guy and this guy are both negative, it will actually return theta 1 in the fourth quadrant, right? So you know the tangent axis looks like that, right? So if both of them are positive, it will actually give you this theta 1, right? If both of them are negative, if you use this function, it will actually, it doesn't know that this guy is negative, but if you actually use this guy, then it will actually return theta 1 to be in the actual proper quadrant, right? If you use this one. All right, deal. So now we found theta 1. How can I find theta 3? Okay, sorry, this guy is theta, cosine theta 3. How can I find theta 3? So if I actually divide this guy over this guy, right, I can actually get cosine or tangent theta 3. Right? So how can I find theta 3? So what I'll do is I want to divide this guy over this guy, right? So I'm going to end up with what? Minus tangent theta 3. You guys agree? So if I divide this guy over this guy, so sine theta 2 and sine theta 2 will disappear. Sine over cosine is minus tangent theta 3. It's going to be equal to what? It's going to be equal to what? Okay. So my y3 is 0 and then my x3. So basically, I would actually need to know these guys, right? So I would actually need to specify a pose, right? For this guy. And based on this, so this will actually also solve the role, right? So what is my x3 to be in this frame? And then what I need to do is I don't actually need to find y3, so I will simply define x3 0, right? And then I can solve y3 0 by doing the cross product between this guy and this guy, right? So I don't need that. So first of all, I need a directional vector. Then I can actually put my x3 0. So where would I like my x3 0 to be, right? And this is obviously free. So my x3 0 will actually define what? It will define the yo, right? It will actually be somehow linked to theta 1, and then it will be linked also to the role. I'm not going to actually get into this, but I will just tell you how you can solve that. So once you have x3 0, you can find y3 0, and then you can actually find this guy by doing these two entries on, this guy would correspond to what? Would be to, so this guy is going to be, what? So this guy is going to be y. So this is the z component, right? So this is the z component of my y-axis, right? What I would like my y vector to be. Divide by what? The z component of my x-axis, right? In the base frame, obviously. Okay, so then my theta 3 is going to be equal to a tangent 2 of, so I can do the minus of them. So minus yz 0 and then xz 0. And what is that guy? This guy is what? After you obtain your y-axis, so we said y30 is actually equal to what? Is equal to the cross product of what? Of z0 or z0 and then x0. Okay, after you actually find y30, you can look into the third component of your z component of this guy, right? And then this is z component of my x0. Okay, and then this is how you can find your theta 3. And then this is how I can find my theta 2. Okay, guys, so you're really kind of not very responsible for doing the inverse kinematics on these guys for now. What is important for you guys is to understand how we actually develop the homogeneous transformation. All right, and if I actually give you these vectors, I may ask you to find these guys, right? But I would actually provide you this vector. I would provide you this vector, or I would provide you a homogeneous transformation or a pose basically, and then I would ask you to find, cosine theta 2, or I would ask you to find, theta 2, theta 1, and then theta 3. All right. So what is really important here is to understand how we actually place the DH transformations, or how we place, DH frames, and how do you actually do the actual homogeneous transformations between all of them, how we calculated this guy, right? What I recommend is that you guys try and then do this in MATLAB on your own, okay? Try to do this in MATLAB and then try to actually solve it. And if you want to kind of get more into it, basically try to actually plot this in MATLAB and then try to vary theta 1, theta 2, theta 3. Try to really see how you actually, to make sure that you actually understand what's actually going on. Okay, so that is really it. Next time we're gonna start inverse kinematics into a more detail. But for now, I'll let you guys sink this in your head, and then I recommend that you guys try to implement this in MATLAB. Do all these transformations in MATLAB symbolically, and then solve them, and then try to see if you can plot the robot just like what we did last time in the MATLAB example. Okay, guys. So that is it for this lecture.